Okay, so last time we ended with this discussion on existence and uniqueness for linear systems. So most important thing was that when you're doing these row reductions, when you're doing the row reduction algorithm, putting something into reduced row echelon form, uh, the entire thing you're looking for to answer the question of whether or not the system is consistent is whether or not there is a row in your echelon form of the matrix that looks like this. Okay, so if you have a row that looks like this, it's a bunch of zeros, and then the last entry is something that's not zero, that is exactly what tells you that the system is inconsistent, right? Because in that, so this is for, remember, this is for the augmented matrix. Okay, this will become specifically important when we start viewing linear systems as matrix equations, because there will be a coefficient matrix and then there will be an augmented matrix. And so those are two different things. It might seem like a really trivial distinction, but it's very important that you distinguish between augmented matrix and the coefficient matrix, because exactly the opposite thing is going to be true for a coefficient matrix if you try to apply this. But in the augmented matrix system, what does this correspond to? This corresponds to an equation in that linear system that says 0 is equal to something that's not 0, right? And it doesn't matter what choices of x you use there, you can't have 0 is equal to something that's not 0. So that's why this immediately leads to an inconsistent system, and in fact, this is exactly the only thing that can go wrong. Okay, so there's not anything else that can go wrong here. This is the single thing that can go wrong. Okay, and of course, when it is consistent, so when this doesn't appear, then you have two options. You have a unique solution, and that happens exactly when there's no free variable. Or you have infinitely many solutions, which is exactly what you get when there is a free variable. If there's at least one free variable, you get infinitely many solutions. You get a different solution for every choice of free variable, okay? And that's a free choice, so infinitely many. All right, so this is very important, this discussion that we've done. And I know that, you know, we've been taking a lot of time here at the beginning, but honestly, if you fully understand this, then everything that follows is essentially just going to be using, it's just going to be using row reduction to put matrices into reduced row echelon form, and then you're done. essentially any question that you want to answer can be answered once you've done that. Okay, so now I want to talk about a topic that's going to be very familiar to pretty much everybody. So this is vectors in, say, R2, but of course it doesn't matter. We're talking about Rn or not. Okay, in fact, maybe I'll convince you by the end of this course that we could just as well have talked about vectors in C2 or Cn. And what I mean by that is I could have used the complex numbers here instead of the reals, and it would have all worked out just fine. So what is a vector in R2? So a vector in R2 is a u sub 1 and u sub 2 entries in a column vector that when I'm writing a vector, because I can't do boldface with my pen, I'm going to put this arrow above it. So this is a vector in R2 where each u1, u2 is a real number. So this is a column vector with 2 entries, or just a vector. Now, maybe in your life you've only seen vector computations be done where you've written a vector as an ordered pair. You might say, hey, wait, that vector u, that looks like the ordered pair u1, u2. That's an ordered pair of real numbers in R2, right? I know what R2 is. R2 is the plane, so it's the coordinate plane of points that are ordered pairs here, u1, u2. Yeah, absolutely. So could you develop everything that we're going to do in this course using this notation instead of this? Absolutely. But we're not going to. Could you have developed everything that we're going to do in this course writing this as a row instead of a column? Yes, but we're not going to. Okay, so you got to make a choice, and this is the choice we're making. So all the vectors we write will be column vectors unless specified otherwise. Okay, so basic things about vectors, right? So two vectors are equal if and only if all corresponding entries are equal. Right? So obviously 2, 1 is equal to 2, 1, but 2, 3 is not equal to 2, 5. Right? So first entries match up, but second entries don't, so these have to match up 100%. Okay, so what does, and of course the corresponding entries have to match up, so like 2, 3 is not equal to 3, 2, obviously, for the same reason. Think about these as ordered pairs, right? So the order actually matters. But you already know all this, so that's why I'm going to quickly go through a lot of this stuff. I want to talk about some basic vector operations. So vector operations. What do those vector operations look like? So I have, I can add 2 vectors. So say u plus v. And when I write a vector and I use this vector symbol, I'm going to assume that this is the notation I'm using. So I'm going to write it out here, but I won't in general. So how do I add 2 vectors? So if I have vectors u plus v, then that's u1, u2 plus v1, v2. And this is done component-wise. So in the first slot, it's the sum of the first two of the things in the first slots in both of these vectors. Same thing for the second slot. Okay. All right. So that's how that goes. But you already know that. You've already seen how to add 2 vectors. So this is how I do u plus v. Okay. All right. Now, you might recall that there is no good interpretation, no single interpretation, I should say, of multiplying 2 vectors, right? So you already are thinking, well, okay, I've got the cross product, but cross product is kind of weird as far as a product goes. It's not even commutative, right? The dot product is very, very, very nice, but of course the dot product doesn't actually return a vector, so it's not a closed binary operation, right? It takes you from the world of vectors to the world of scalars, okay, which we'll talk about. But there is one type of multiplication that's allowed, but it's not between vectors. It's a scalar and a vector, all right? So scalar multiplication is another one. So one is vector addition. And of course, vector addition leads to vector subtraction, if you like. You can subtract two vectors from one another by adding scalar multiple of -1 times a vector to another vector. So what's scalar multiplication? So let C be some real number, i.e. a scalar. Okay. Now, for us, scalars are going to be real numbers, and scalars you've encountered might be real numbers. But as I'll mention later, there's no reason why you can't take your scalars to be complex numbers. The idea is that they are a number, they're not a vector. Okay. So let's see, be a real number. So we call this a scalar, and the reason we call this a scalar is because scalar multiplication scales the vector in question. So Cu is Cu1, Cu2. So it literally takes every entry and multiplies it by C. Okay. All right, so C is called a scalar, and this is called scalar multiplication. Okay, so let's quickly do example. So here's an example. Let U be 2, 3. Let V be -5, 1. I want to compute, say, U plus V, 5U, and we'll say 2U plus -3V. Okay. All right, so U plus V is, in each slot I have 2 plus -5, and in the second slot I have 3 plus 1. So this is -3, 4 is U plus V. 5U is 5 times 2, 5 times 3, so this is 10, 15. And lastly, 2U plus -3V is 2U. So 2U is 4, 6 plus -3 times V is -5, 1. So this is going to be 4 plus 15 and 6 plus -3. So this is 19, 3. Okay, so all of you have done basic computations with vectors before like this. Let's just remind you of the geometric meaning of what's going on, because a lot of times intuitively it makes a lot more sense to think of things geometrically. So recall, vectors, and this is true in dimensions. I know I'm doing it in the plane. The reason why the plane example is so important is because intuitively what's going on doesn't change when the dimension increases. Like, as far as geometrically what you're thinking about, more or less the same thing is happening. Sometimes you have to adjust to whatever the analogous situation is in the higher dimensional case. But for much of what you want to do, it is sufficient to understand what's happening in the plane, and what's nice about that is you can draw that on paper. Right? So recall, vectors in Rn are the same as points in Rn. So vectors and points are the same. Okay, so that's true when n is equal to 2. So vectors in R2 are the same thing as points in R2. So to see that, let's look at my vectors u. So 1 will be 2, 1. Let's let v be the vector 3, minus 1, and let w be the vector, say, minus 2, minus 1. Okay. So then geometrically, what are those vectors? Those vectors are just these points. So there's here's 1, 2, 3, 4. Oh, I only need 3 here. 2, 3. Okay. So the vector 2, 1 is here. There's u. Okay. What do I mean by that? So there's u. V is 3, minus 1. So here's v. And w is minus 2, minus 1. So here's w. But what do I mean vectors are points? You all know that the first time you ever encountered vectors, a vector is described as a pair of quantities, a length and a direction, right? Where does the length and where does the direction come from for these things? Well, these points specify an arrow starting at the origin and pointing towards those points. Right, there you go. So there are the vectors associated to those points, right, in the classical sense. So there you go. Here's why vectors are points. And of course this works in space just as well, and it works in higher dimensional Rns as well. Okay. Now there's some geometric meaning for some of these things that we'll look at really quickly. So geometric meaning of operations. So what's the geometric meaning of vector operations? So u plus v is the vector corresponding to the fourth vertex in the parallelogram. So this is in R2 still. This is the fourth vertex in the parallelogram determined by u, v, and 0. I haven't mentioned that yet. Oh, I'm off the page. So the geometric meaning of operations: u plus v is the vector corresponding to the fourth vertex in the parallelogram determined by u, v, and 0. Let's go back for a second. I didn't mention the 0 vector. What is the 0 vector? The 0 vector is the vector that contains nothing but zeros. Okay. So we'll worry about being very, very thorough with this stuff axiomatically when we do chapter 4. Chapter 4 has us treating vector spaces completely axiomatically, meaning we're going to start with a list of vector space axioms and we're going to kind of proceed from there. So I'm going to save that discussion till later. But this is called the 0 vector because when it comes to, say, vector addition, this is the 0 object, right? So note, for instance, u plus the 0 vector is always u for any vector u. Right, so this is the 0 vector. Okay, for higher dimensional spaces, the 0 vector has more entries, but the idea is exactly the same. It is just the vector that contains nothing but zeros. Okay. All right, so going back here. Of course, if you're thinking geometrically about where the 0 vector is located, it's located at the origin. Okay, so it is the vector determined by the origin. It starts at the origin and points towards the origin, so that doesn't leave a whole lot up to the imagination. Okay, what do I mean by this? This picture, this can be a little bit confusing. The idea here is I have vector u and I have vector v. These are really bad drawings here. I have my 0 vector at 0, so that's my third vertex. Where does this fourth vertex show up? Well, there's a couple ways you could do this. You could think about taking the vector u and sliding it along to the end of vector v, or taking vector v and sliding it along to the end of vector u. Either way you do that, you complete a parallelogram. And the parallelogram you complete has some vertex that is u plus v. And of course the vector associated to it looks like that. Now that looks like a pretty bad picture, so how about we look at this picture in the textbook. So there, right? There's a picture in the textbook. Shows exactly what it is that's going on here. So I have two vectors, u, v. I add them, I get this diagonal of the parallelogram. So in fact, geometrically, if you want u minus v, you look at the other diagonal. So how does this work? So here's an example explicitly working this out. You can take vectors u, v, you sum them, and you get minus 4, 3 here, which turns out to be exactly fit into this picture. Okay, so if you have a look at that. All right, so then that is geometric meaning of addition. What's the geometric meaning of scaling? So this takes care of vector addition. So geometric meaning of scalar multiplication is exactly what you think it is. So the geometric meaning of scalar multiplication, so let u be, say, 3 minus 1. So write, say, minus 2 u minus u. So that's minus 1 times u, 2u, 3u, etc. Okay, well, if I just write these things out, then what do I get? So minus 2u is minus 6, 2, and minus u is minus 3, 1, and 2u is 6 minus 2, and 3u is 9 minus 3, and so on. Right? So this is what I get. But what does this look like if I actually write this out? So here's my picture. 3 minus 1, here's my u. Right? But if that's what u looks like, then what about 2u? Well, 2u is going to point in the same direction, but it's going to be twice as long. So this is 2u. And what about 3u? 3u is again going to point in the same direction, but it's going to be 3 times as long. So this whole thing is going to be 3u. Okay. What about minus u? Minus u is going to have the same length as u because I'm scaling by minus 1. I'm not changing the length, but I'm changing the direction. So it has the same length as u, but it points in the opposite direction. So this is minus u. Minus 2u points in the opposite direction of u and has twice the length. All right. So looking at this picture, I am naturally led to the following question. What geometric object is the set containing all scalar multiples of a given non-zero vector? The answer is that's a line. Right? That's a line. Okay, so if you want a nicer looking picture, right, here's one. Let me get that up close. You can see what it is that's going on there. So here's 0u, you can think of if you like. Here's a u. There's 2u. Minus 2/3 u, of course, is just it's scaled in not quite as nice a way, but it's the same idea. So it would point in the opposite direction of u, and it would be 2/3 as long. Okay. Now, so natural question, what object is the set of all scalar multiples of a given non-zero, that's important, that is an important assumption, vector? And the answer to that is a line, as you can see here. So I could do this just using integer multiples of a vector, but of course you're allowed to multiply by any scalar, so you don't have to restrict yourself to integer multiples here. So what object is a set of all scalar multiples of a given non-zero vector? It's a line like this. Why did I have to include the word non-zero that I've underlined here? Because if this vector that I started with was 0, then any scalar multiple of that thing would still be 0, and so we would just be stuck at the origin. So in that case, that object would be a point, a single point. All right, so keeping track of those cases, making sure that you're not in some degenerate case where something like that happens is important in this, because as you might have heard, this course uses a lot of true false trickery when it comes to asking you a bunch of conceptual questions that are true false. Now it'll be a little bit different this semester because it will be a little bit less pressure on you because all of your stuff is going to be take home, but still there's going to be a ton of true false things. You're going to have to parse through all those words carefully. Now so a vectors in R3, I can do the same thing. So a vector in R3, I don't care, it looks like this, right? It's U1, U2, U3. Vector operations are defined similarly. The pictures work out similarly, it's just not as nice to draw. But it works out in the exact same way. In fact, if I go here, a vector A scaled by 2 is exactly the same thing. It's just I have to draw it in 3D, which just kind of sucks, right? But the exact same thing is going on here, and that's why it's important to understand the 2D case, because that allows you to actually draw in any of this. And of course, the general case, vectors in Rn. So my vector u would have n entries, so u1, u2, all the way down to u sub n. Okay, that's it. And each of these things, so u sub I is in R here, u sub I is in R. Okay, now I am not going to go over this as a list. I'm just going to flash it on the screen real quick. We will go over this axiomatically in chapter 4, so that's why there's no point doing it now. But you see, here is a list of algebraic properties of Rn. So these vector additions of vector addition and scalar multiplication satisfy this list of properties. These are known as the vector space axioms. Okay, so these are vector space axioms. This is the statement that Rn is a vector space. Okay. And again, it mentions here, for simplicity of notation, u plus minus 1v is just written as u minus v. So addition of vectors gives you subtraction of vectors in that way. So these are all the various properties that you'll need for these operations. But as I said, you already know those things. I'm not going to list them out exhaustively. Okay. Now the next thing, you may not have seen this exact terminology before. This is the notion of linear combinations. Okay, so here's the definition, and the definition is the definition of linear combinations. Okay, so what is a linear combination? So given vectors in Rn, so v sub 1, v sub 2, up to say v sub p in Rn, and given scalars c sub 1, c sub 2, up to c sub p in R, okay, define the vector y by y is, when I write colon equals sign, that means what follows is the definition of this quantity. This is not something standard. You're not going to use y here. I'm just doing it in this definition. So c sub 1, v sub 1 plus c sub 2, v sub 2, and so on, all the way up to c sub p, v sub p, okay, is called a linear combination. So this is called a linear combination of the vectors v sub 1 through v sub p with weights c sub 1 through c sub p. Okay. Now, the main reason for mentioning those algebraic properties of the vector sum and scalar multiplication first is that these associative properties means I don't have to write a bunch of stupid parentheses here. I can just, there's no ambiguity writing this thing out. So what is linear combination? Linear combination is just I have some arbitrary combination of those operations we just talked about. So we just talked about what it meant to add a bunch of vectors together. Well, I started saying what it meant to add two vectors together, but of course, if I can add two by the associative property, I can add three, and I don't have to worry about what order those parentheses go in. I can ignore the parentheses. So I can add multiple vectors together. And of course, I could also perform scalar multiplication on each of those things, each of those terms separately. So this is just literally a combination of those vector operations. So then, seeing what the geometric picture is, so here, let me bring this a little bit closer. So imagine taking vectors. So for instance, in this case, vector v sub 1, which is minus 1, 1, and v sub 2, which is 2, 1, and then looking at the linear combinations as scalars go over all the reals. What is this picture you get here? Right? Well, you're going to get, so if you just keep it simple and you look at these given, so the integer multiples of these vectors v1 and v2, and then you can look at rational multiples plus some things here that get you these like fractional vertex points between this. This is like a lattice, right? So this is like some nice parallelogram grid that you've put on R2 from this operation. So we're going to talk about this a lot throughout the whole course, basically what this operation gives you. So the question is, what does any of this have to do with what we've done so far? So big question. What does any of this have to do with what we've done so far? Okay. The answer is, consider the following example. Which I'm not going to be able to fit on this page, but I'll fit it on the next one. Okay. So, the quick answer. The quick answer to this is that basically this is going to allow us to recast linear systems using different language, but it is going to, of course, be the exact same answer, or it's going to have the exact same solution. Okay. So, here's the example in question. So let a sub 1, a sub 2, and b be the following vectors. So I'm going to be reading them column-wise because they're vectors. So 1, minus 2, minus 5. A sub 2 is 2, 5, 6. And b is 7, 4, minus 3. Okay. So determine whether b can be written as a linear combination of a1 and a2. Okay, i.e., that is, determine if there exist weights x sub 1 and x sub 2 such that x sub 1 times the vector a sub 1 plus x sub 2 times the vector a sub 2 is equal to b. This is a vector equation. So this is a vector equation. So if this vector equation has a solution, find it. So technically I just asked whether or not it was possible that you could write it like this, but I want to actually find a specific solution here. Okay, so let's do this, all right? So rewriting this vector equation using these vectors here, this is x sub 1 times the vector a1, so that's 1, minus 2, minus 5, plus x sub 2 times the vector 2, 5, 6 is equal to the vector 7, 4, minus 3. All right, so here's a sub 1, here's a sub 2, and here's b. Okay. Okay. All right. So, what does this mean? Let's actually, fold all this stuff in using our definition of all these operations that we just talked about. So, of course, this is a scalar times a vector, so it just scales each of those entries by that amount. So this is x sub 1 minus 2x sub 1 minus 5x sub 1 plus 2x sub 2, 5x sub 2, 6x sub 2. And all that's equal to 7, 4, minus 3. And of course, continuing on here, now adding these two vectors, I get the vector equation x sub 1 plus 2x sub 2. And in the next slot, minus 2x sub 1 plus 5x sub 2. And in the last slot, minus 5x sub 1 plus 6x sub 2. And that is equal to 7, 4, minus 3. Okay? But now you see what's happening here. All right, so continuing on, I don't want to take this entirely off the page, so I'll just move it up here for the time being. So here's where we are. Okay, oh, there we go. Okay. So, but two vectors are equal if and only if each of their entries, each of their corresponding entries are equal. Then this takes this vector equation, turns it into a linear system. X sub 1 plus 2x sub 2 is equal to 7 minus 2. X sub 1 plus 5 x sub 2 is equal to 4. And minus 5 x sub 1 plus 6 x sub 2 is equal to minus 3. All those have to be true simultaneously, and so this is just a linear system, right? So this is a linear system. So then this naturally leads you to ask the following question, which is every vector equation like this equivalent to a linear system? The answer is yes. It didn't matter what these numbers were. I could have, if instead of having these specific numbers, I had generic A, B, C, D, E, F here, then I get the exact same thing. I get a completely generic linear system of this form. Okay. So how do I solve a linear system? Now that I've put this in terms of linear system, I know how to solve this, right? So the augmented matrix is 1, 2, 7, minus 2, 5, 4, minus 5, 6, minus 3. Okay, so there's my augmented matrix. All right, putting this into reduced row echelon form. So I'll write out a couple and then I'm just going to skip. So I'll do 2 times row 1 plus row 2. We'll zero that entry out. And 5 times row 1 plus row 3. We'll zero that entry out. So what I get here, this is 1, 2, 7. Here, this would be 0. Let's see, 9 and 18. And then this last one is 0, 16, 32. Okay. And so quickly then what do I get here? I continue on. This is let's scale this by 1/9. So this is 1/9 times row 2. So 1/9 times row 2 is, so this is 1, 2, 7, 0, 1, 2, 0, 16, 32. I can clearly zero out these two entries by multiplying row 2 by minus 16 and adding it to row 3. So minus 16 times row 2 plus row 3. Replacing row 3 gives me 1, 2, 7, 0, 1, 2, 0, 0, 0. So I have a row of zeros there. And then zeroing out, so this is almost in reduced row echelon form, so all I have to do is zero out this entry. So this is minus 2 times that thing. So this is minus 2 times row 2 plus row 1. Gives me 1, 0, 3. 0, 1, 2, 0, 0, 0. So there it is. All right. Thus, the solution to this linear system, I'll call it star. So the solution to star is x sub 1 is equal to 3 and x sub 2 is equal to 2. But what was this original question? Let's go back to my original question. My original question was whether given these three vectors, so a sub 1, a sub 2, and b, whether or not b could be written as a linear combination of these two. That is, whether or not this vector equation where x sub 1 and x sub 2 are the weights had a solution. Turns out, yes, it has a solution. So if x sub 1 is 3 and x sub 2 is 2, then this has a solution. So i.e., thus we have solved, so b is equal to 3 times a sub 1 plus 2 times a sub 2, and this could be checked. Okay, so this could be checked. If you take 3, multiply by a sub 1, add to that 2 times a sub 2, you get b. All right, so that is our answer to that. Okay. So, thus B is a linear combination. It is a lincom of a sub 1 and a sub 2. And that is the specific linear combination. Those are the weights. Now, as I said before, can you always do this? The answer is yes. You can always do this. Okay. And to really codify that fact, right, to make it rock solid, let's write out exactly what I mean by that. So questions about whether or not a given vector is a linear combination of some specified set of vectors is equivalent to solving a vector equation, which is equivalent to solving a matrix equation, or sorry, well, that's also true, but a linear system. Okay, so here is a very important fact that basically just says that everything we did today for vector equations is actually just another way of looking at linear systems. So a vector equation that looks like x sub 1 times a1 plus x sub 2 times a2 and so on, all the way up to x sub n times a sub n is equal to the vector b, has the same solution set as the linear system whose augmented matrix is a sub 1, a sub 2, and so on, all the way up to a sub n, and the last column is b. So when we write a matrix like this, what we mean is that the columns are these vectors. Okay, so maybe I should write separately. This is the matrix whose first column is a sub 1, second column is a sub 2, and so on, and last column is b. So this is what we mean when we write this. This is just very convenient notation for us. Okay, so in particular, B can be written as a linear combination of the vectors a sub 1 through a sub n if and only if there exists a solution to the linear system corresponding to this matrix. Okay. So this is a very important fact. Okay. All right. So, what else needs to be said here? So, because of this fact, because a vector equation has the same solution set as a linear system that its augmented matrix looks like this. And because this is equivalent to asking when a vector can be written as a linear combination of some other vectors, this notion of thinking of all the possible linear combinations of some set of vectors is very important to studying linear systems, vector equations, and ultimately we'll see matrix equations here in a second. So here's a definition that specifies that. So if we have vectors v sub 1 through v sub p are in Rn, then the set of all linear combinations of those vectors is denoted by the span of those vectors and is called the subset of Rn spanned by those vectors v1 to vp. So the span of a set of vectors is a very important thing. So i.e. span of v1 to vp is the collection or the set of all vectors that can be written in the form C1 V1. I'll go ahead and actually write the next terms out. So C2 V2 plus C3 V3 all the way up to CP VP. Okay, where C sub 1 through C sub P are scalars. Okay. Thus, so this is the definition. Why this definition is important is that it allows us to actually ask the same question we were talking about earlier more conveniently. So thus, asking whether a vector B is in the span of some set of vectors. So asking whether or not some vector v is in the span of vectors v1 through vp is the same as asking whether the vector equation x sub 1 v sub 1 plus x sub 2 v sub 2 and so on up to x sub p v sub p is equal to b has a solution. Which is the same as asking whether the linear system with augmented matrix v sub 1, v sub 2 up to v sub p b has a solution. Okay. Okay. So I think that is where we'll stop for now. So I will, on Monday, we'll finish up our discussion of span for now and move on to the next bit in chapter 1. Okay. So anyway, so that's it for now. I'll see you all on Monday.